Conditional probability is probability based on a previous event. So this right here, this notation means probability of B happening given that A has already happened. So the probability that B will occur given the event A. So one formula that we can use is the probability of B given A is probability of A and B happening at the same time divided by the probability of A. Now, I'll use this formula mostly in charts. So I have this first example where I don't really need to use this example, but this is an example of conditional probability. So conditional probability, suppose there are 2 grape juice boxes and 4 apple juice boxes in the refrigerator. If you choose 2 juice boxes at random to drink, what is the probability that they're both apple? So this is going to be, you're going to take the probability that you're going to have an apple juice box, and you're going to multiply it by the probability that you have an apple juice box after an apple juice box is gone. That's really what's happening is you're taking the first probability that's an apple, which is 2 or which is 4 out of 6, and then you're getting rid of an apple juice box. So now you only have 3 and there's 5 total. So you're going to multiply it. So this is 12 out of 30, which reduces to, you can divide both of these by 6, so it would be 2/5. So you can write probability as a percent, as a decimal, or as a fraction. So either one of these is correct. So we can use this formula up here when we're looking at probability in charts. So example 2, did you do a household chore last night? So first of all, there's 15 males because 7 plus 8 is 15. There's 13 females. 7 plus 6 is 13. So therefore, we're going to have 28 total people. Of the people that there's 14 people that did a household chore, and there's 14 people that did not. So this notation over here means find the probability that the person was male given that they said yes, they did a household chore. So what I think about is this being the denominator. Yes is your denominator. So how many people said yes? 14. Of those people, how many were male and said yes? That's 7. So the answer is 50%. For the second one, find the probability they did not do a household chore given they were females. So you should find the total females, which is 13. Of these 13, how many said no? So it's 6. So it's 6 out of 13. So you can either write 6 out of 13, or you can do 6 divided by 13 on your calculator and get about 46%. Sometimes it's not written with that notation. It's just find the probability the student is male given that they did a household chore last night. So this is the same thing as probability of male given yes. Well, that's the same answer as up here. So it's 50%, but sometimes it's written out. Okay, example 3. Looking at this chart, so number of times students visiting, tutoring, whether they're full-time or part-time students, and the data is broken up. And we actually already have the totals here nicely. Sometimes you want to go through in total, just like we did up here. So number 1, find probability that a student went one or fewer times, given they're a full-time student. So we're only going to look for a denominator is full-time students. So there's 45 full-time students. Now, of those 45, 12 of them went one or fewer. So I'm going to divide 12 by 45 and get about 27%. So the second one, what is the probability that a student is part-time? So I'll write it like this. Probability part-time given they visited tutoring 4 or more times. So I'm going to put my denominator as the 4 or more times, which is 14. And my numerator is going to be, of these 14 people, how many were part-time? So that's 6. So 6 divided by 14 is about 43%. Number 3, find the probability a person is part-time and they visit 2 to 3 times. This doesn't have the keyword given. So what's the probability? How many people total, of those total people, so there's 58 total people, how many of them are part-time and they visit 2 or 3 times? So in the chart, I'm going to look for part-time and visiting 2 or 3 times. So that's a 5. So it's 5 out of 58. So the key word was and. It means it's happened at the same time. That's different than the given up here. So I do 5 divided by 58, and I get about 9%. And then number 4, find the probability they visit 4 or more times given they're a full-time student. So full-time student is going to be your denominator, which is 45. Of those, how many go 4 or more times? 8. So it's 8 out of 45, which is about 18%. Another way we can represent conditional probability is in a tree diagram. So example 4, of those attending prom, 65% seniors and the rest are juniors. This is going to be our first, these are 2 branches of our tree diagram. So I'm going to branch out, we have seniors and we have juniors. And I'm actually going to put the percents right here. So seniors, 0.65. If the rest are juniors, that means that 35% are juniors. Then, of the seniors, 60% are female and 40% are male. So from the senior branch, I'm going to branch out and do 60% female and 40% male. And of the juniors, 53% are female. So 53% female, which would mean 47% are male. I'll erase that. So 47% are male. So I'm breaking up my chart like that. So draw a tree diagram at right. So I have my tree diagram. Then, the reason I like to use this tree diagram is if you have to answer a question, what's the probability a person at the prom is a senior male? What you're going to do is you're going to multiply the probability that somebody is a senior with the probability that somebody's male. So you're looking at this branch right here. So it's going to be 0.65, because that's the probability they're senior, times 0.4. So it's kind of a visual way to see it in the male. So it's going to be 0.65 times 0.4, and it's 26% exactly. So if you're looking at each branch, this would be, if you multiply 0.65 times 0.6, that's the probability a person at the prom is a senior female. If you multiply 0.65 times 0.4, that's the probability somebody is a senior male. And then if you multiply 0.35 times 0.53, that's a probability a junior is female, etc. So all of these, at the end, if you add up each of these probabilities that you multiplied across, you get 100%. Second one, what's the probability a person at the prom is female? So, all right, so we just got to figure out, we have two situations of female. You can be a senior female or you can be a junior female. So I'm going to multiply 0.65 times 6, or 0.65 times 0.6, and I get 0.39. Then I multiply 0.35 times 0.53, and I get 0.855. So if I add those two together, I'm going to get the percent of females, which is about 57.55%. So I'll round to about 58%. So this is about 58%. So make sure you can draw a tree diagram to represent it. Example 5, we're actually already given a tree diagram, and it's about cancer screening. So I'm going to zoom in and explain a little bit. So in this diagram, of the population, 0.001 is the decimal that represents have cancer in this population. So 0.999 of the people do not have cancer. So this is equivalent to 0.1%, by the way, and this is equivalent to 99.9% in this particular population. So sometimes when you get cancer screening, when people are screened for cancer, they might have a positive result, but they might not actually have cancer. So I'm going to go through and explain what each of these means. So this means these people in this top line have cancer and they test positive for cancer. This middle part right here, if I multiplied these two, this would mean that they had or they didn't have, I think I might have misspoke here. They can have cancer, but their test came back at negative. So even though they had cancer or they have cancer, it doesn't show on the test that they have cancer. So that's a really sad case of somebody going to the doctor, thinking something's not right with them, and then only to find out that they test negative, but however, they really do have cancer. So they're not able to get the treatment. Of this situation right here, these people don't have cancer, but they actually test positive. So you go to the doctor, you actually don't have cancer, but your screen shows up that you have cancer. That can actually happen. That's called a false positive, if you've ever heard that in the medical field. And then right here, no cancer, test negative. So that's most of the people don't have cancer, and when they go to a cancer test, they test negative. So using this chart, find the probability a person tests positive for cancer given that they have cancer. This is a situation where you really want to read the word given. So this means that we're only going to look at the people that have cancer. So only look at here, what is the probability they test positive? Well, it's 0.99. So there's no multiplication in this situation. The second one, find the probability somebody has cancer. So I'm going to look at, well, this one's already in our chart too. The probability they have cancer is just going to be 0.001. And then the next one, find the probability a person tests positive for cancer and does not have cancer. So that's a scary situation where you go into the doctor and they say you have cancer, but you actually don't have cancer. So test positive for cancer and doesn't have cancer. So no cancer, test positive. So it's an and. So I'm going to multiply 0.999 times 0.05. So what's the likelihood of that? So 0.999 times 0.05 is about 5% again. Because it's 0.0499, so I'll put about 5%. Find the probability a person tests positive for cancer and has cancer. So test positive for cancer and has cancer. So I'm going to multiply 0.001 times 0.99. So 0.001 times 0.99 is, on my calculator, I don't know if you do on your calculator, but 9.9 times e to the negative 4. But that just means we need to move our decimal over 4 times. So 1, 2, 3, 4. So it's 0.12399.